Welcome to a new deep dive. Today, we're tackling one of the universe's most mind-bending phenomena, black holes. You sent us an incredible stack of sort. It's really fascinating stuff, from the basics to some cutting-edge research. Our mission is to sort of cut through the cosmic clutter for you. Think of this as your quick guide to really getting these things. We'll unpack why they're called black, but, they can also be these incredibly powerful cosmic lighthouses. So let's start at the beginning. Based on the material you sent, what exactly is a black hole? The definition seems to be a region where a huge amount of mass is squeezed into an incredibly tiny space, creating gravity so strong that nothing, not even light, can get out, which is why they're, well, invisible, right?
Exactly. And what's really fascinating is how they just completely change our picture of reality. The whole idea comes straight from Einstein's general relativity, which is says gravity isn't really a force pulling things. It's more like massive objects actually warping space-time itself, like a bowling ball on a trampoline. And black holes. They're the most extreme warping imaginable. Space-time is basically infinitely curved there. And that extreme curve leads to the event horizon. That's the key boundary. It's not like a solid surface you could hit or anything. It's the point where the escape velocity, the speed you need to get away, becomes faster than the speed of light. So space-time itself is kind of flowing inwards faster than light can flow outwards, which does make you wonder what happens if you cross that line.
Right, and deep inside. Your sources mention this singularity. A point of infinite density. It sounds like the place where all our current physics, totally breaks down. It's basically pointing towards, well, new physics we haven't figured out yet. Okay, so given how extreme they are they all the same? Or are there different kinds? The sources you sent highlight something pretty amazing. Despite being so complex, they're defined by just three simple things: mass, spin, and electric charge. That's the no-hair theorem, isn't it? What's the deal with that?
Yeah, the no-hair theorem, it's kind of mind-bending. It basically says that once a black hole forms, it sort of forgets all the details about what made it, like what kind of star collapsed, its composition. All that complex information just seems to vanish. All that's left, observationally, are those three properties: how heavy it is, how fast it's spinning, and its charge. And this apparent loss of information is actually a huge puzzle in physics. It's called the information paradox. And thinking bigger picture, they come in different flavors too. You've got your stellar mass black holes. These typically form when a really massive star dies and collapses, maybe a few times the mass of our sun. Then there are the monsters, supermassive black holes, millions, even billions of times the sun's mass. We find these at the heart of almost every big galaxy, including our own Milky Way. That's Sagittarius A. There's also been this kind of gap in the middle intermediate mass black holes. We're only just starting to find good evidence for those, especially thanks to things like gravitational waves.
And I saw mentions of theoretical ones, too. Primordial black holes, potentially formed right back at the Big Bang, and maybe even being dark matter.
That's a really exciting possibility. If they formed super early, they could be tiny, and that might explain some, or maybe even all, of that mysterious dark matter we can't see. It's still theoretical, but people are looking.
Okay, wow. And the supermassive ones. You mentioned they're not just sitting there, they actually shape their galaxies.
Yeah.
How does that work?
Yeah, they're not passive at all. They co-evolve with their galaxies through something called feedback. Basically, as gas falls towards the black hole, it heats up incredibly hot in what's called an accretion disk just outside the event horizon. This disk can blast out powerful jets and winds of energy and particles, and these outflows can push gas out of the galaxy, stopping stars from forming, or sometimes they can compress gas clouds elsewhere and actually trigger star formation. So they're like cosmic thermostats or architects really shaping how the galaxy grows.
That's incredible. Okay, but the big question, if light can't escape, how on earth do we know they're there?
Yeah.
How do we find something invisible?
Right, that's the clever part. It's mostly about seeing their effects on stuff around them. Gravitational wave astronomy is huge now. Observatories like LIGO and Virgo can hear the ripples in space-time when two black holes spiral into each other and merge. That first detection, GW150914, was absolutely historic. It was like hearing the universe itself vibrate from these collisions. Direct proof. And we also look with regular telescopes, but not at the black hole itself. We look at that superheated gas and the accretion disk around it. It glows incredibly brightly in X-rays and radio waves before it vanishes over the edge. We can also track stars moving very strangely, orbiting something invisible but really massive. That's how we mapped out Sagittarius A in our galaxy center. Oh, and gravitational lensing, too. Their immense gravity can bend light from objects behind them, distorting the view like a lens.
And then there was that image, the Event Horizon Telescope picture of the black hole in M87. It wasn't really a photo of the black hole, was it? More like its shadow. It's that dark circle surrounded by the glowing gas.
Yeah.
It's kind of beautifully ironic. Their blackness makes them visible in a way.
Exactly. It's the silhouette. You're seeing the shadow cast by the event horizon against the backdrop of that incredibly bright, hot gas swirling just outside it. It's the closest we've ever come to directly seeing that boundary, that point of no return. It's stunning proof of that extreme space-time warping.
What a journey we've taken. From, bending space-time itself to literally shaping galaxies, black holes really push our understanding.
They absolutely do. They're like natural laboratories for testing the limits of physics, trying to mesh general relativity with quantum mechanics, maybe even explaining dark matter. They're crucial.